Topic is binary heap. In this topic, we are going to learn these things. What is a heap? I'll explain what is a heap first. Then, how to insert in a heap, how to delete any value or any element from the heap. Then, what is heap sort? The next, there is a procedure called Heapify. We will learn about that procedure. And finally, priority queues. Priority queues already we have discussed something in queues topic. So that time I said I'll explain afterwards. So here it comes, priority queues. Let us start with the definition of heap. The very first condition of heap is it is a complete binary tree. So what is a complete binary tree? If a binary tree is represented in an array, then there should not be any blank spaces in between the elements. Right now there are no blank spaces, so this is a complete binary tree. If I remove this value 10, then this place is left vacant, blank, because these elements are stored based on these formulas. Left child at 2i and right child at 2i plus 1. This blank space is there, so this is not a complete binary tree. I'll put back that value 10. So this is a complete binary tree. This is the definition already we have seen. And I said that this is also called as almost complete sometime. So it is complete or almost complete. So heap must be a complete binary tree. This is the first condition. It must satisfy this condition. Reason, binary heaps are implemented using array. If we want, we can follow linked representation also, but mostly in the algorithms, they are used in the form of an array. So the foremost condition that it must be complete, that is, there should not be any gaps in between the elements. So this is the first condition. Second condition, there are two possibilities or two options are there in second condition. First one is, every node should have an element greater than or equal to all its descendants. Greater than or equal to means duplicates are also allowed, right? This is not binary search tree, this is heap. Duplicates are also allowed. Every node should have the element greater than or equal to its descendants. So here already I have greater element, 30 is greater than all these descendants. Now let us look at this, 15 is greater than its descendant, 20 is greater than its descendant. So if this condition is satisfied, then it is called as max heap. Now another option is, every node is having elements smaller than or equal to all its descendants. So like 5 is smaller than all its descendants. 15 is smaller than its children, that is descendants. So this type of heap is called as min heap. So I repeat once again, heap is a complete binary tree satisfying any one of the condition, either as max heap or as min heap. And heaps are represented mostly using array. Now next important thing about heap. Heap is a complete binary tree. As it is complete binary tree, always the height of a binary tree will be log n only. The height of a tree will not increase unnecessarily. For example, this is a binary tree. This is complete binary tree. This is all right. This is also complete. We will not add nodes here. This is not complete. If I add node here, it is not complete. So height will not increase unnecessarily. We cannot insert any node here unless we have filled this node. And now when we have this node, then the next node should be on this side. It should not be a left child of this one. It should not go to next level. So height of a tree will not increase unnecessarily. Always the height will be log n only. This is a very important property, that height of a complete binary tree is always log n. So also height of a heap is also log n. Heap is not useful for searching purpose, right? It is not useful for searching purpose. What is the use? We will see it afterwards. Let us learn how to insert in a heap. So I'll be showing it on max heap. Whatever we learn in max heap, same procedure is applicable for min heap also. So we will be learning just upon max heap. So let us learn how to insert. So for insertion, already I have taken a max heap here, and that is represented in an array. In array, it is looking like this. It's a complete binary tree. And the array indices are starting from 1 on. Like when we are using the formula 2i and 2i plus 1, for that array indices must start from 1 onwards. So that's why I have taken array index from 1 onwards. Now let us insert. The element that I want to insert is 40. This is the element that I want to insert. Now tell me when it should come. This is a max heap and the root should have the largest element or greatest element. So 40 should be kept in root, isn't it? The very first idea what students get is this one. 40 should be kept here. Then where to send 30? Okay, push it down. Which side? This side, that side. No, that is not the procedure. We don't directly insert it in root. Now see the procedure I am explaining. Insert a key element in an array at a next free space. So where is the next free space? Here. Insert an element here. At this place. Here. So in a heap we always insert in next free space. Reason, we want to maintain a complete binary tree. If we store it in root, then root should be pushed down somewhere else. So you may not get a complete binary tree. So the foremost condition, it must be complete binary tree. So when the element is inserted, then there should not be any gaps. That is the reason it is inserted here. Then where it will be in this diagrammatic representation? 40 is a left child of 5. How? See, who is the parent of 8, index 8? 8 by 2 gives what? 4. What is the value there? 5. So for 5, 2 into 4 is 8, right? So this is left child of 5. It's a left child of. And in other words, see, in a complete binary tree, we try to fill the elements from left to right. So in this level, all 4 elements are completed. Next level, where I should insert an element? Here only. So this is the place where 40. Now next, 40 is inserted. But is it a max heap? Every node should have the element greater than all its descendants. Oh, this is smaller. This is not a max heap. Okay, so insert the element, move it up until it becomes a max heap. So what I have to do here? So rearrange the elements to make it as max heap. So how to rearrange? Let us start. Compare this 40 with its parent. 40 is greater than 50. So keep 40 in some temporary variable. Let us say like this. Hold it there. Then copy that 5 here. Then go to this place. Compare 40 with this one. So 40 is greater than this one also. So it's still compared with the parent. So bring 20 down. Right? Now 40 is here. So I will not copy, just I will hold it here. Then again compare with its parent. So again 40 is greater than that one also. So move 30 down at this place. Then above this one, there is nothing. So we have reached. Now copy 40 there. 40 is copied here. So this is how when 40 was inserted, it was compared with its parent and its parent and its parent until it has adjusted itself. Now the elements are rearranged to form a max heap. Check it. 30 is greater than all these. 15, this part is not disturbed at all. Then 20 is greater than this. It's perfect. 40 is greater than all. Yes, it's a max heap. Now let us look at here in an array, how it looks like in an array. See this element, I will take 40 in some temporary variable. Compare the element 40 with its parent here. That is 8 by 2, 4. Compare this element. 5 with this 40. So 5 is smaller, 40 is greater. So copy this 5 here. Then bring I to this place. Then standing here, again compare with the parent. So 4 and again compare with the parent. So 4 by 2 is 2. This compared with this element. So 20 is smaller than 40 or 40 is greater than 20. Copy this 20 here. So this place is vacant now. Bring I here. Again 2 by 2, 1. Parent is this one. Compare this element with 40. So 30 is smaller than 40 or 40 is greater. So this is greater. So we have moved the element as long as this element was greater. So 30 will be moved to this location wherever I is pointing. 30. Go to its parent. So 2 by 2 is 1. So I moves here. Now there is no parent for this one. This is root because I became 1. So 1 is the starting index. Copy that 40 here. This is how inserting is done. I will insert one more element. And so now 40 is inserted and the heap size has increased from 7 to 8 now. So heap is from 1 to 8. There are total 8 elements in a heap. Quickly I will insert one more element. Let us insert 35. I want to insert 35. 35, new element. So it is stored in a complete binary tree order. So it comes as a right child of this 20. 35 is here. So the procedure is Compare newly inserted element with its parent. So this is greater than the parent. So keep 35 here. So copy 20 at this place. So bring the parent value at this place. Then compare 35 with its parent. So 35 is greater than that one also. So bring that 30 at this place. Then compare 35 with its parent. So 35 is not greater than 40. So this is the place where 35 should be stored. Copy 35. So insert an element in next complete binary order and compare with the parent and compare with the ancestors and try to rearrange the elements. The procedure is very simple. Let us do it in an array. Element is 35. Take it here and start I from here. Right? Now, who is the parent? 9 by 2 is 4. This is the parent. So compare with the parent. 20 is smaller than this one. So move 20 here at this place. Then bring I here. This is at index 4. So where is the parent? 4 by 2. 2. 35 is greater than this one. So move 30 also to this place wherever I is pointing. Then move I to this place. Now from here compare with the parent. So what is the index 2? 2 by 2. Parent is what? 2 by 2. 1. This one. Compare with this one. No, 35 is smaller than this one. So this is the new place for 35. So 35 is inserted. And the heap size is now 9. There are total 9 elements. Array size is 10 but the heap size is 9. Now let me write the procedure for inserting in a heap. That is the procedure for rearranging the elements. I will write on the procedure here. So insert function I have written. Insert function is taking a parameter that is array where heap is stored. So example, this array, I have changed the name A. So like A is an array, this array. Then N is the index of recently stored element. So how we call that insert is, first of all, I will store the value here, for example, 50. Then I will call that insert function. So what is N? N is this one, index 10, where the newly inserted value is there. Okay. Then what I have to do? I have to take an integer pointer I here so that it can go on checking the elements. And also I should take this in a temporary variable. So I need some variable temp and also I is initialized to 0. I should take this element in a variable temp 50. So 50 is gone. Sorry. 50 is copied here and I is pointing here. So I should point on N. Then this temp I should copy here. Temp assign A of N. That is the last index. Now what I have to do? Compare the temp element with the parent of this index I. If a temp is greater, copy that element at A of I. Go on doing that same thing. How long? Until you get some element that is greater than temp, stop. Or else you have reached 1. So as long as I is greater than 1, I should continue. So this copying can be done using loop, that is while loop. So I will write on the loop. So while I is greater than 1 and temp value, the value that we have inserted, is greater than its parent. So parent means I by 2. Integer division, it will take floor value. So A of I by 2, parent's value. If so, if its parent value is smaller, then we copy that element here. So from A of I by 2, we will copy it in A of I. Copy the element from A of I by 2 to I. Then bring I here at this place. So I assign I by 2, I assign I by 2, will bring it here. That same procedure is repeated. When the loop, while loop stops, when it stops, either you have any value that is greater than temp or I has reached 1. Then copy this temp wherever I is pointing. Temporary value, the value in a temporary variable, that is the new element that we are inserting, is copied at A of I. That's all. This is the procedure. So how to call this one? First of all, you write down the value in an array, that is in a heap array, and then call this insert function by passing this index. It will rearrange. Actually, it is rearranging the values. So this is the insert function. Now analysis. How much time it is taking for inserting one element in a heap? We always insert a new element at the leaf, as a leaf, last level, right? Then we will try to arrange the elements. So for the arrangement, the element will move up At most it may reach root. So it is moving up level by level. So total, how much time it is taking, how much work we are doing. So it is taking log n time. So it is taking time depending on the height of a tree. So what is the height of a complete binary tree? Always log n. Yes. So insertion time is always log n. So for inserting one element, it takes log n time. See, I have explained you this with respect to working what we have done diagrammatically or graphically. But if you want to know what is the time taken from the code, if you want to read, see, this while loop is starting from n, and every time that value of I is divided and divided by 2 every time, again and again. So what will be the time? So how many times it get divided by 2? Log n base 2 times, log n base 2 times. So from the loop also, from the code also, program code also, we can understand that it is taking log n base 2 time. So next we have to learn how to create a heap, that we will look at in the next video. So here we will learn how to create a heap for given elements. In the previous video already we have learned how to insert one element in a heap. So using that same basic idea, I will extend it and show you how to create a heap. See, here I have an example. This is a max heap with the 3 elements, 30, 20, 10. 30 is greater than these two. So yes, it's a max heap, and also it's a complete binary. It is there in the array. So this is in heap. So these 3 elements are forming a heap. Then this insert function, this procedure we have already seen how it works. If I insert a new element like 40 here, then I can arrange this element within these elements to form a heap of 4 elements. So this will try to adjust by checking with the parents and adjusting the element at a proper place. So we know well how it gets adjusted. I'm not going to adjust it now. We know how it works, right? It compares with the parent and adjust it. So for one element it works. Now let me extend the idea. I will insert 40, 15, 12 and 25. See, this portion is a heap and these elements are not in heap. Heap is ending till here, only 3 elements. What about these elements? They are present in the array, but they are not in heap. So is it possible to insert all these elements one by one? Yes, I can insert. First insert 40, so heap size will become 4. Then insert 15, heap size become 5. So one by one I can insert all the elements in a heap. So it is just like from this side include an element on this side to form a heap. So it means from right hand side include an element in a left hand side heap. So one by one I can insert the elements. So this means that these 3 elements were also inserted like that only. Yes. So then how many elements will be there initially in a heap? One element. The very first element is heap. So this is the idea. One by one we insert the element from right hand side to left hand side and go on creating a heap. So we don't need any extra array for creating a heap. Within an array only elements can be adjusted to form a heap. So that's how this is called as in place heap creation. When it is happening inside same array, we call it as in place. So heap can be created in place. So I will take few elements and I will try to show you how a heap is generated. Now let us see the procedure for creating a heap. See, already I have 7 elements and the first element is in heap. Obviously, if nothing is in the heap, then at least first element is in a heap. Ignore all of them, just one element, nothing to compare with anybody. So it is heap, right? The font size I kept it small because I need more space. Now let us insert second element in a heap. So the next element that I will insert is 20. So insert 20 in a heap. So when I insert 20, diagrammatically if you see 10, 20 come as a left child of this one and 20 is greater than 10. So 20 should move up and 10 should come in its place of 20. Then how it looks like in an array, 20 will be here and 10 will be here. Now till here it is heap, then remaining elements are as it is. This comparison we can see it here that 20 is compared with the 10. So 20 goes here and 10 comes to in its place. So this is the result after inserting 20. Now next element is 30. So third step, I will say insert 30. So diagrammatically how it looks like. Right now tree is 20, 10, 20 and 10. So 30 is on this side, right? So 30 is newly inserted. Compare with the parent. So 30 is greater than the parent. So 30 goes to the parent's place and 20 will come in the place of 30. So this is moved or swapped. So this has happened when we were inserting 30. So it means 30 was compared with the parent. So this is index 3. 3 by 2 is 1. So it was compared with this one. So what is the resultant array? Elements in a heap are 30, 10 and 20. Heap is still here and the remaining elements 25, 5, 40 and 35 are as it is. So this is after inserting 30. Next I have to insert 25. So insert 25, right? Inserting 25 means where 25 will come? 25 will come as a left child of 10 as per complete binary order. 30, 10, 25, 25 newly inserted. Now newly inserted compare with the parent. So this is greater than parent and more with the parent. No, this is not greater than 30. So it will be swapped with a 10. So the resultant tree will be 30 is not modified. At this place comes 25 and here is a 10 and this is 20. How it is done in an array? 25 is index 4, so 4 is compared with the 10. So yes, 25 is greater than 10, so it is swapped. And further if it is compared, this is not greater than 30. So it is swapped only with the 10, so this is the result. So how the array looks like now? Till here is heap, 4 elements are in a heap and after 4th element, remaining elements are 5, 40 and 35. So 5, 40 and 35. These are yet to be inserted. Next is 5. Fifth step, insert 5. Where it will be in a tree? So this is the previous tree. Now we are including 5. So 5 comes here, right? Now compare this 5 with the parent. This is the parent. So it's not greater than parent. So no change as it is. It is in its right place. So the array looks like this. So the array elements will be as it is 30, 25, 20, 10 and 5. Heap is till here 5 elements and remaining 40 and 35 as it is. Next insert next element 40. 40. When we are inserting 40, 40 gets inserted as a left child of 20. So I will draw it. So 40 is here. It will be compared with 20. So it is greater than 20. So it will be swapped. And further compared with the parent. So it is greater than 30 also. So 40 will move up until it reaches root. So 40 reaches root. And left side is not modified. At right side 30 comes here and 20 come as left child. So the resultant array, there is no space. I will draw it here. Elements in heap are 40, 25, 30, 10, 5, 20. And the last element remaining that has to be inserted is 35. So when this 40 was inserted, it was compared with the parent 6 by 2, that is 3. Then again its parent, that is 3 by 2 is 1. So it was compared like this and it was swapped. Now last element 35, where it will come? It will come as a right child of 30. So I'll show it here. So this is 35. 35 is newly inserted. It is compared with the parent. So it is bigger than this one, greater than this one. So it has to be swapped. And with its parent, no, it is not greater than that. So the resultant tree is, so this is a resultant tree, final heap, right? Final heap. So the elements in a array will be 40, 25, 35, 10, 5, 20, 30. So these are the elements in a heap. Finally a heap is created. So you can observe that initially all the elements were simply given in an array. They were not in a heap. So we assume that first element is in a heap. Then we started taking the elements from right hand side and inserting them on left side. Like first 20, then 30, then 25, then 5, then 40, then finally 35. So one by one we have taken the element and inserted it on left hand side heap to create a heap. And all the adjustments are done in the same array A, right? Same array A. We don't need any extra array. Heap is created in place. So here I will write on the procedure for creating a heap. So here I have a function for creating a heap. So array of elements is with this function only. So I have an array, starting index is 0, so there I did not use anything, I just kept a 0 there. So the elements are starting from index 1 onwards. This is index 0, this is 1, 2, 7. Then what I have to do, first element assume that it is in heap only. Second element insert, that is 20, insert, then 30, insert. So I should start from index 2. Insert an element index 2, insert an element from index 3, then 4, then 5. So for that, I is taken here. I is starting from index 2 onwards. And it's going up to index 7. Every time an element is inserted by comparing with the parent, so this is done by this insert function. So create heap is calling insert function by passing array and I. So first time I is 2. So this second element is inserted. I was 3. So this third element. I was 4. Fourth element will be inserted. Then when I becomes 5, fifth element. So sixth element. Like this, all the elements will be inserted up to the last element 7. So major work is done there by insert function. But this create heap function is utilizing that function for creating a heap. How much it... So that's all about creating a heap. Now analysis. What is the time taken for creating a heap? Creating a heap means inserting the elements one by one. So for one element, what is the time taken? Log n. For n elements, how much time? N log n. So the time is n log n. So the time for creating a heap is n log n. See, all these things we have studied for max heap. If you want to change it for min heap, then just you have to change the condition. Temp is less than I by 2, just less than, then this becomes completely for min heap. So just change of condition will change the procedure for min heap. So as I said, what we are learning on max heap, same thing applies on min heap also. Now our next topic will be deletion from heap. Now let us look at delete operation from heap. Already a max heap is given here and I want to delete. So which element I should delete? Shall I delete 25? Shall I delete 35? No. The very important thing. From heap you can delete only root element. Which element is there in the root? Largest element. This is max heap. So largest element. So when you want to delete, you can delete only largest element, you cannot delete any other element. So a hint here, it means you can delete highest priority element. Yes, you can only delete highest priority element. Yes. Now, how to delete that 40? Okay, I will take out 40 from here. 40 is gone. Let us take it in some temporary variable, hold it for some time. Then which element should come here? Common sense says that 35 is greater, so it should come here. Okay, I will send 35 there. Then who should come here? 15 is greater, so 15 should go there. Okay, 15 will go there. Then see the problem. Is it a heap? It is not a complete binary tree. It's not a complete binary tree. So if you try to adjust the element like this, it will not be a complete binary tree. Then what is the solution? Look at this once again. I'll put back the elements, 15 as it is, 35 as it is. This place is vacant, 40 is gone. Copy the last element in complete binary tree order at this place. So bring 5 at this place. Bring 5 here. Yes, that's perfect. So 5 is removed from here. So when the root goes out, the last element in complete binary tree should take its place. So I'll remove this from the diagram. This is gone. Now this is a complete binary tree but not a max heap. So I have to adjust the element, rearrange the element so that it becomes a max heap. Before showing you how to adjust the element, let us do the same thing in an array. I will take out this value 40, that is root, the very first value. It is at index 1 in variable x. And I will bring this 5 at this place. So 5 is copied here. Now heap is till index 6. 7th location is empty. Now, how to adjust these elements to form a max heap? For this, the procedure is compare children of new root. Children, compare who is greater. This one is greater. This one is greater. Then compare this one with the new root. So root is smaller than this one. So interchange. 5 comes here. 35 goes there. Then continue. From here, compare its children. Which child is greater? This is greater. So interchange 5 with this one. 5 comes here. 15 goes there. Now from this place, there is no left child or right child for this node. So stop. So the procedure was compare the children. First find out which child is greater. Then compare with the element. If the element is smaller than any of the child, then interchange with that child. So now it is perfectly adjusted. It is forming a heap, max heap once again. So here if I show it in an array, then this is the element that I have to adjust. Compare its children. So who are children? If this is I, then 2i, 2i plus 1. Compare these two. If I is at 1, compare its left child and right child. This is greater. Then compare this child with the parent. So parent is smaller than the child. So interchange them. So this becomes 35 and this becomes 5. This is one step that we have seen it here, right? 5 came here that time. Now again its children. This is 2. So 4 and 5. Compare these two children. Now let us say I is here. I is at this place. So compare its left child and right child. Right. So let us take J. Which is greater? This is greater. So let J be at that same place. So interchange the value at I and J. So 15 comes here and 5 is copied here. So these are interchange. Then take I to the place of J. This is the new location of the element that we are adjusting. We have adjusted 5, right? Now where is the left child of this one? So that is 8. 2 4 8. So 8 is outside the heap locations. So that's all. Stop. So this is how deletion works. I will write on the procedure. So here is a delete function which is taking an array, this array, and n is the size, that is last index 7. So this last index element I will take it in variable x. A of n is taken in x. This element is deleted. Then copy the last element at this place. A of nth element is copied at first place, that is index 1. Then we need I on the element that we are adjusting and j on its left child. So I is at index 1, j is at its left child. Now the procedure is repeating. So I have to write a loop. So I will write while loop. What I have to do every time? Compare left child and right child. Whichever child is greater, let j point on that child. See, wherever j, suppose j is pointing here at 4, then right child is next element only. So a of j plus 1, if it is greater than j, then move j to right child. Like j was here, so I was here, and element 5 was here and 15 here. Compare a of I with a of j. If a of I is smaller, then interchange a of I and a of j. If the parent element is smaller than child element, then interchange parent and child. And also bring I at that place of j. So I will come at the place of j. Elements are swapped. Then j should go to its left child. So j should move on to 2 into j. If the parent element is not less than child element, if it is greater or equal, so we don't have to swap and we don't have to go further. Stop. So I will say break. That's all. These are the steps. Compare left child and compare right child. If it is greater than left child, then move j and compare with the element a of I with a of j. If element is smaller, then swap with a of j. Then take I on j and also move j to the left child. So this loop should continue how long? Until you reach the end of this heap. So what is the end of the heap? The last index was 7, so it should be 6. So if last index was n, then it should be n minus 1. So while j is less than n minus 1, we have to continue. That's all with the delete. Now I have not closed delete. I have to show you something more. So this procedure you have to trace it by yourself once, then you can remember and again you can write on by yourself. right? So take some bigger size heap, you take some 15-20 elements and then you try it. You can clearly see the things working. So that's all we have completed. Delete. I will repeat the points once again. So always root element can be deleted and the last element in the complete binary tree will take its place, and then we adjust the element by sending it downwards towards its children. So whichever child is, if a child is greater, then that child will interchange with the parent, and we try to adjust the element. So we have adjusted 5 just now. So similarly, if I delete once again, I can delete only 35, then who will take its place? 25. 25 will go there and 25 will be adjusted. That's it. So this is how we can delete as many elements as you want. Now listen, very important thing. See, we deleted 40. 40 was gone. And this is a new heap with 6 elements. Earlier 7 elements were there. Now the heap size is 6 only. But in an array, one space is vacant. Is it a part of heap? No, that is outside heap. So the element that I have deleted, shall I keep it there? Yes, I can keep it. Is it a part of heap? No, this is outside element. It's not in a heap. 40 is stored at a free space after deletion, right? Now delete again. Which element you get? 35. What will be the size of a heap? 5. This place will be free. Shall I store 35 there? Yes. Then next, which one will be deleted? 30. Next, 25. Then 15. Then 10. Then 5. What happens to the array? Sorted. Yes. Yes. This is heap sort. This is heap sort. So what is heap sort? From the heap you to go on deleting the elements, and as you go on deleting the elements one by one, you get a free space at the end of an array. Use that free space for storing the deleted element. So the elements will be getting arranged from last element onwards. That is, they will be arranged in descending order from the right hand side onwards. So finally they will be in ascending order from left hand side onwards. That's it. This is the heap sort. Let me show you one thing. See, in this delete, I said I did not close the bracket. What I will do is, deleted element was in X. I will copy it at this last free space. So last free space is N. So at A of N, I will copy X and then close. So what this delete function is doing, deleting an element and copying it at last place. Now I will show you heap sort. Heap sort. First step, create heap of n elements. Create heap of n elements. First create heap. Already in the previous video we have seen how to create a heap by inserting elements one by one. Elements are in the array only. Same array, the elements will be inserted. How to create a heap we saw. Create a heap. Then after that, go on deleting the elements from the heap one by one. And start copying the elements at the free spaces which we are obtaining after deletion. Copy the element at free space. So delete and copy, that's all. Delete n elements one by one. That's it. So create a heap of n elements, then delete the elements one by one. That's all. It became a heap sort. Create heap of n elements, delete all the elements. The deleted elements, start arranging them. It's a heap sort. So for understanding heap sort, we must know how to create a heap and how to delete the elements from the heap. Then heap sort is nothing. See, it is just like we have some set of elements. So we are inserting in the heap, dipping in the heap and taking out the elements from the heap. They are sorted. So that's all about heap sort. Now let us do some analysis. How much time that create heap was taking? Create heap was taking n log n time. Yes. Then how much time one delete is taking? One delete means the element is adjusted. So how much time it is taking depends on the height. So for one element, deletion of one element, log n. For deletion of all n elements, n log n. So deleting all elements also, n log n. So total time taken by heap sort is 2n log n. So this is order of n log n. So it is order of n log n. I will write on the complete program. for insert also, delete and create heap, and deleting heap. Then also finally I will show you heap sort. So that's all finished. In this video we'll be looking at heap program for C language. So in this program I will be writing a function for inserting as well as deleting, as well as I will show you heap sort. So let us call this as heap. Create a program. So a new project is created. As we have discussed, I will take one array for heap. So I'll call the array name as h for heap, and I'll take the size as 7. So as we have discussed, for implementing a heap using an array, we will take an array, and size I will not mention. Directly I will initialize some elements. See, the 0th index we are not using it, so I will skip that one. So for that I will set it as 0. Now rest I will set the elements. So total 8 elements I have taken, including 0. So the array size is 8 and I have only 7 elements in a heap. These are the elements in a heap. 0 is ignorable. We will not be using this location at all. Now I have randomly taken some elements here. Now let us write a insert function for a heap. Void insert. It should take an heap array as well as the element index of an element that we want to insert. So let us call the index of that element as n. So here inside I will take some variables, that is I starts from n, and also one temporary variable. Then that temporary variable should have a of I value. That is what we have to insert in a heap. Now we have to compare and switch the element or swap the element until it reaches root or until it fits in its right place. So for that we have taken a while loop while I is greater than 1 and the temp is greater than a of I by 2. So we'll be comparing it to parent, and if it is greater than parent, then we will copy the parent value. If it is greater than parent, then we will move the parent. So at a of I, we will copy the element from a of I by 2. Then I should be moved to parent. By 2 will make it move to the parent. And finally, when we have reached at the last place, means we got a right place for this temp element that we are inserting, then we will copy the element at a of I as temp. That's all. This is insert. Now, as already I have taken some elements in an array, I can insert them one by one. So first I will insert 5 in a heap. So right now heap is having only one element, let us say 2. Then I will insert 5, so 5 will go on this side. Then 8 I will insert, then 9. So let us see what will happen if I insert all these elements one by one. So let us call insert heap, and first element that I will insert it as index 2. So here I'll mention index 2. Then I'll copy this and paste it, and next I will insert an element at index 3. This I can do it using for loop also, but I just want to show you step by step. Just see what happens. Then fifth index. So let us check till here what happens. So I am inserting 5, 8, 9, 4 and 10. Here I'll put a breakpoint, then I will run. Oh, there's a mistake. Yes, here I have given the name of an array as h. Okay, I will change the name to a. Here the parameter was h, but I was using a. Now it's perfect. So you can watch in this debug area. Right now array is containing the element 0, 2, 5, 8, 9, 4, 10. So if I continue executing, 5 is inserted first, so 5 should come at the place of 2. Yes, 5 has came at the place of 2. Next element to be inserted is third element, that is element 8. So it will come up to root. So yes, you can see that 8 has came into root. The next is largest element 9, so it will come in the root. Yes, 9 has came in the root. and 8 has become its left child and 5 is the right child. Then 4, when I inserted 4, 4 remains in its own place. Yes, 4 has remained in its own place. So you can see that the elements are inserted in a heap one by one. Right now this array is not a heap, but by inserting these elements one by one on the left hand side, this is forming a heap. I'll remove this breakpoint. I'll stop the program. I will insert all these elements one by one using a loop. So let us take a variable I, and using for loop, I will insert the element. So I have to insert the element from second element onwards. So I is less than or equal to the last index is 7, then I plus plus. So here instead of 2, I will take it as I. So only one insert function is sufficient because it will be repeated using for loop. Now this will be inserting all the elements one by one. Here I will change the values. The one I will take the example that we have already seen on the whiteboard. That is a program for creating a that is a procedure for creating a max heap. So I will write down the same set of values that are 10, 20, 30, 25, 5 and 40 and 35. Yeah, these are the elements that I have taken on whiteboard. Then after forming a heap, these are the list of elements that I should have in an array. When that are converted into a heap, I should have the elements like this: 40, 25, 35, 10, 5, 20 and 30. This is what the result should be. Once this has converted into a max heap, then the array should have these elements. So I have changed these elements that I have taken the example from the whiteboard. So I have changed these elements. I have taken the same example which we have seen on whiteboard for creating a max heap. So let us run this and see. I should have the elements sort arranged in this form. So for that, I will use a for loop for displaying all these elements. So I will display all of them. For index starting from 1 onwards, I is less than or equal to 7, then I plus plus. Let us print them. Percentile D, that is h of I. And at the end, a new line. Let us run this. Yes, I got the elements in the same order. See, this has formed a Yes, I got the elements in the same order. This has formed a max heap. Now next, let us look at a function for deleting one element from a heap. So here I will write a function for delete. Delete function should take an array. I'll give the name as A and the number of elements, that is size of heap, the exact size of heap. We need the last index. Now I need some variables I, j and x. So x assign the element that we want to delete is a of 1. The first element will be deleted. We cannot delete any other element from heap. In x, I will take the last element, that is a of n, the last element, and at the first location I will copy the element from the last location, that is x, that I have taken just now. So the last element is copied at the first place. Then I should start from first element, that is what we have to adjust, and j should be pointing on left child of I, that is I into 2. So this is the left child of I. Now we have to adjust this element. For adjustment, we will run a while loop while j is less than n. Now, as we have reduced one element, the size of the array, that is size of the heap, has reduced by 1, so it is j minus 1. Then every time we have to check whether the left child, that is where j is pointing, or the right child, who is greater. So here I will check if a of j is So here I will check if a of j plus 1, that is the right child, is greater than the left child currently wherever j is pointing, then move j to next location, that is j plus 1. Let it point on the right child. Then check the parent value where I is pointing, and the value of a child where j is pointing. So if a of I is smaller than a of j, then interchange these elements. So for interchanging these elements, I need a temporary variable. So I will take some temporary variable. Then a of I is copied in temp. Then in a of I, copy the element from a of j. Then in a of j, copy the element from temp. So this all swapping is done. Then I should come upon j, that is the child, and this j should move on to left child, 2 into j. This will go on the left child. That's all. And if I is not less, means it is properly adjusted. So simply say break, that is stop the loop. That's it. And here I have used one more variable, that is temp. So I have declared a variable temp. Now the value that we have deleted was a1. So I have not taken it in any variable. So let us declare one variable val, and in that val, that is deleted value, we will take the value from a of 1. So this is the deleted value. And at the end, I will also return val, that is deleted value. That's it. So the same code I have written, what I have explained on whiteboard. So let us see whether it works. So after creating a heap, I will perform delete operation. So directly I will call it in printf. Deleted value is %d, a new line, call delete function by passing heap array, and the number of elements are 7. Then so right now, after forming a heap, the root element will be 40. So 40 should be deleted. And inside this delete operation, we are arranging the deleted element at the last, that is at this index. So here we should get 40, and these elements must be forming heap. So this 40 is deleted and it should be copied at the last place, and the rest of the elements must be forming heap. Let us run this. Yes, deleted element is 40. Okay, new root is 35. Oh, this 30 is still there. This is not replaced by 40. So let us check in the code. We have copied it there. Yeah, last element we brought it here, but we did not copy this first element at last place. So I will do that one also. After copying this, I will say a of n should be assigned with the deleted value. Now let us run this one. Yes, 40 is copied at the last place. So this delete function is deleting an element, and also it is keeping the deleted element at the last place. Let us try to delete one more element. I'll copy this and paste it. And now the heap size is not 7, heap size is 6. So let us run this now. 35 should be deleted. Yes, first time 40 is deleted and the second time 35 is deleted. And the heap is from 30 to last element is 5. And these two elements, 35 and 40, the deleted elements are arranged like this. So that's how the elements are deleted. Now I will call a delete function using a loop. So I will delete all the elements one by one. So for I assign n, that is 7, n is 7, and I is greater than 1, I should stop when it has become 1, then I minus minus. And call delete function by passing heap and I. Then afterwards, I will display all the elements. So let us see what happens. Oh, elements are sorted. Yes, that's it. This is heap sort. So heap sort, you can see that insert all the elements one by one in a heap and delete all the elements one by one from heap. And inside this delete operation only, the deleted elements, I am storing them at the last place, that is free space in an array. This is the statement which is storing the element at the last place. So that's all about heap sort. So you can practice this program. So that's all. This is a program for max heap, and also it is for heap sort. Let us learn about topic Heapify. Heapify is a procedure related to creation of heap, not just insertion of one element. Inserting all the elements in a heap one by one and creating a heap. So it is related to creation of heap. So for understanding Heapify, let us observe insert procedure and delete procedure, which we have already studied in previous videos. So from these two procedures, we observe something that will help us understand Heapify. So let us start. See, this is a max heap. And in max heap, how to do insert we have already seen. Suppose I want to insert 45. Where it should be inserted? It should be inserted in the next complete binary order position. So this is the next free space in complete binary order. This is complete binary but not max heap because 45 is here. So what we do is compare with the parent and its parent and its parent and move 45 towards root because this is the largest element here. So we have adjusted the element. So how adjustment is done? By sending the element from leaf towards root. So only this is important. In insertion, elements are adjusted by sending an element from leaf towards root. Come to this, delete. I want to delete element. So we know very well that only the root element will go out 40, and who will take the place of this element? The last element in complete binary will take its place. So 5 will come in its place and 5 is removed from here. Now this is a complete binary tree but not a max heap. So we try to adjust. How? We compare with the child. This is a greater child, so we swap it with this one. Then again we compare with the child, so this is greater out of these two, so swap it this one. So we'll bring down the element from root towards leaf. This is important. Now we are ready to understand. See, here also in inserting also we are adjusting the element to form a max heap. Here also we are adjusting the element to form a max heap. But the direction of adjustment is from leaf towards root. Here direction of adjustment is from root towards leaf. That's what. Direction of adjustment is different. This is enough for me to explain you Heapify. So you can have a look once again. Direction of adjustment is different. Now I'll remove this and explain you Heapify. Now let us understand how Heapify works. So for that, I have taken array of elements. So here also I have same elements. I have array of elements. I have to create a heap out of these elements. And the create heap procedure, already we have seen it. I have taken few elements and I have created a heap by inserting one element at a time. So let us first look at that procedure and then we will see what Heapify is. So I am going to create a heap. So let us look at create heap. See, these elements, they are not in a heap, but I will draw a binary tree for this one. So first element is 5, then its left child is a 10, then right child is 30 and 20 on its left. So level by level I have filled all these elements by following the formula 2i plus 1. Now I have a binary tree. This is not a max heap. I have to make it as a max heap. So how the create heap procedure was working? It was assuming that this is already in heap, just one element 5. So it was considering that heap is still here. Then insert the right hand side element on left hand side heap. So insert this one. So insert this one by swapping the element. 10 will go up and 5 will come down. So I will work out on this. So 10 will move up and 5 come down. Then it will insert this one. 30 is greater than 10. So 30 moves up and 10 comes down. Then it will come to this element. 20 is greater than this but less than 30. So 20 moves till here and 5 comes here. Then 35 is greater than this. So that 20 will come this side and 35 will move up. And 35 is greater than this one also. 35 will move up and 30 will come down. Then 40 is inserted. 40 is greater than this one and this one also. So 40 moves up till here. Then 35 comes here and 10 comes here. Now 15 is smaller than this one, so no change at all. So this is how we have swapped so many elements. And you can observe that every time I was adjusting the element by sending it towards root. This was create heap procedure and the time taken by this was n log n, because the log n is the time taken by one element, maximum time to reach till root, and n elements are inserted. So time is n log n for creating a heap. Now let us see Heapify and understand how it is faster. Same way I will generate a binary tree first. Let us see how Heapify works. First, comparatively I will show you. I have generated a binary tree. Now let us see Heapify procedure. Watch carefully. See here, the first root element that was 5 initially, I said only that element is in heap. Then other element I started inserting it and I was moving upwards. I will not start from this first element, I will start from last element. Means not from 5, I will start from 15. This was left to right. In Heapify, we will start from right to left. So we will start from this element. Watch it. I will not compare with the parent. So I will not work from leads towards root, but I will work from this element downwards. Means from root towards leaf. That's in deletion we saw. That procedure I will perform. See here the elements were compared with the parent, but here the elements we will compare them with children. Let me do it now. 15, is it having any children? So imagine only 15 is there. Alone, single element. It's a heap. It's a heap. Because nothing is there below. Forget about all the elements, just 15. There are no children. So it's adjusted. It's a heap. Finish. Don't have to do anything. Then 40. Below 40, nothing is there. So from 40 onwards, if you look downwards, 40 is in a heap. Alone 40. Right? Ignore all of them. Then from 35, look downwards. Assume that 35 is a root of a tree. There is nothing in down in its children. So it is a heap. Then 20 is also a heap. Then come to 30. See, 15, 40, 35, 20, 15, 40, 35, 20. Then we are on 30. Till now I have not done any modification. Watch this. 30. Check here. Compare with the children. Oh, this is smaller than this child. So send 40 up and bring 30 down. Just look at these elements. It's a heap. Finished. Now come to this element. So we'll be looking at only these elements. Compare with the children. This child is greater. So 10 is smaller than that. So send 35 there and bring 10 down. It's a heap. Just look at this portion. Yes, it's a heap. Then go to this element, the very first element. Check with the children. This child is greater. So send 40 up and 5 down. Then compare with the children. Send 30 up and bring 5 down. That's all. This is a max heap. Max heap. How many adjustments? Very few adjustments I have done. Here a lot of adjustments I did. No doubt the heaps that we got are not same. We are not bothered about that. We want max heap. Is it max heap or not? Yes, it's a max heap. Every element, every node is having element greater than all its children. This is having greater than all its, this is greater than all its children. That's enough. It's a max heap. So the procedure works in opposite direction from a node towards its children. So this is the fastest method for creating a heap, either min heap or max heap. So I have shown it for max heap. So this procedure analytically takes order of n time. So this procedure analytically takes order of n times. This is much faster because half of the elements we are not processing, because half of the elements will be definitely leaf. So leaves we don't have to process. Half of the element only we have to process. We process only 3 elements. We have adjusted only 3 elements. So that's how time is n, order of n. So this is a faster method for creating a heap. That's all about Heapify. The topic is binary heap as priority queues. So first let us understand what are priority queues. It is related to insertion and deletion of elements. So elements will have their priority and they are inserted along with the priority. Then when we are deleting, always highest priority element will be deleted. So the most important thing is always we want highest priority element. Example of elements. These are the elements. Where are the priority? Number itself is a priority. Like this is 4. Priority is 4. 9. Priority is 9. 5. Priority 5. So the number itself is the priority. So it means fixed priorities are not there. Whatever the number may be, that is the priority. Then who is of higher priority? Or the smallest one here is 2. 2 is of highest priority or largest number 20 is of highest priority. Which one is highest priority? Whichever one you like. but decide beforehand. You say that no larger number higher priority. Okay, so the highest priority element is 20, then 18, then 15, then 10, then 9 and so on. If you say no, I select that smallest number having higher priority, then highest priority element is 2, then 4, then 6 and so on. So we have to decide beforehand. So I have decided that larger the element, higher the priority. Larger the element, higher the priority. Now let us see how I can implement priority queue. I have the set of elements and an array. I want them to be inserted in the array. Then when I delete, I want to delete them based on the highest priority. So let us insert and also delete. I will insert the elements. Just watch. First element I want to insert. Okay, 4 is inserted. The next element I want to insert. 9 is inserted. 5. Then how much time insert is taking? Order of 1. Constant time. 10. Write down 10 here. 6. Write down 6 here. 20. Write down 20 here. 8. Write down 8 here. Like this I can simply copy the element. Now I want to delete. Delete. Okay, as I said that deletion means always you can delete highest priority element. So who is having highest priority element? Larger the element, higher the priority. Which is larger? Search and find out. Search and find out the maximum element in the entire array. Then I came to know that okay, 20 is greater. So then delete the element. So for after deletion also I should shift the element, right? Because this space will be vacant. So first of all I have to find out, search, that itself will take order of n time. Then shifting also plus n plus n, this is 2n, so it is order of n. So maximum, the time for searching is actually finding maximum. It will take all n elements. I have to check all n elements, then only I can say so and so is maximum. Shifting, maximum n elements will be shifted, right? Maximum n shifting. Minimum 0 shifting also possible. So the total time is 2n, maximum time, so it is order of n. So mainly finding maximum itself is order of n. Now the problem. What is the problem? Insertion taking constant time, deletion taking order of n time. Yes. Why not deletion is also taking order of 1 time? Not possible. Not possible. Is there any other way possible? Can I sort them and store them? You can sort them and store so that the largest element is at the end. I can delete it quickly. Deletion will take 1. Then insertion to keep them in sorted order, that will take order of n time. There is no way to reduce the time. Definitely one of the operation is going to take order of n time. So no solution. Then I have another solution. Watch it here. These elements are there. Make a max heap for this element. Insert the element 4. I am showing only diagrammatically. I am not taking an array. Then insert 9 here. So 9 will move up and 4 will come down. Then insert 5. 5 on this side. This is smaller. Yes. 10. 10 comes this side. So 10 is greater than 4 and greater than 9 also. So 10 will move here and the 9 will come at this place and 4 copied here. Then 6 is coming on this side. This is smaller, no problem. 20 on this side. 20 is greater than both of these. So 20 moves up and 10 comes to this place and 5 comes here. Anyway, remaining elements I don't have to show. I am creating heap. Which heap? Max heap. How much time it takes for insert? We have learned this. How much time? Log n time. Yes, log n time. Then I want to delete. Which element should be deleted from the priority queue? Highest priority element. Who was the highest priority element in this list? 20. Because larger the number, higher the priority. So which element will be deleted from heap? Root element only. So what is the root element? 20 is the root element. That is of maximum priority. Yes. If I delete now, only maximum priority element will be deleted. Yes. Heap is helping us to implement priority queue. Yes. So how much time it takes for deleting any element from heap? We have already studied this. This is also log n. So So insertion is also log n, deletion is also log n. Log n is much less than n. Remember this, log n is a small value compared to n. So both insert and delete takes log n time. So insertion is also faster, deletion is also faster. Because when you delete, always highest priority element is deleted. So heap is a best suitable data structure for implementing priority queues. Otherwise, you can implement them like this in an array. If you are doing it simply like an array of elements, then these are the times. Now that is balanced. Both are taking log n, right? That is balanced time. Distributed. Time is distributed now. Now one more last thing. If I say no, smaller element is having higher priority, then use min heap. I am using max heap. This is max heap. This is max heap. If you say no, smaller element higher priority, use min heap. That's why we have two types of heap, min heap or max heap. Both are for priority queue. If your priorities are like larger number higher priority, go for max heap. If your priorities are like smaller number higher priority, go for min heap. So that's all about priority queue using binary heap.